Mars hangs there. A tiny, rusty pinprick in the vast black quilt of the night sky. For millennia, humans have stared up at it, their necks craned, all wild speculation. We gave it the name of a war god, conflict, fire. Through smudged early telescope lenses, we thought we saw canals, elaborate waterways. We dreamed of Martian cities, strange beings, a distorted mirror of our own. Our journey to Mars has been like climbing a very tall, very rickety ladder. Each rung represents a mission, a technological leap that built upon the successes and failures of the one before it. The lowest rungs were the flyby missions of the 1960s, like Mariner 4. These were the space-age equivalent of driving past a stranger's house and snapping a quick, blurry photo. The goal was simple: just get there and take a look. Mariner 4 gave us our first 22 close-up pictures of another planet. They were shocking. They revealed a surface that looked more like the Moon than Earth, pockmarked with craters. This wasn't the Mars of science fiction. It was something new, something real and geologically ancient. It taught us that Mars was a world shaped by impacts from space. The next rung on the ladder involved getting into orbit. Instead of just speeding past, missions like Mariner 9 in 1971 settled in for a long stay, circling the planet like a patient bird of prey. When Mariner 9 arrived, a global dust storm completely obscured the surface. But as the dust settled, it revealed a world of incredible diversity. It unveiled gigantic volcanoes, including Olympus Mons, the largest in the solar system, and a colossal canyon system, Valles Marineris. For the first time, we saw a world with a complex geological history, a place that had been active and dynamic, not just a static, cratered ball. Once we knew we could land, we wanted to move. A stationary lander is like being stuck in one spot on a visit to a new country. You can only learn so much about the place. The solution was to put wheels on our laboratories, creating the era of the Mars rovers. These robotic geologists became our proxies on the Red Planet, tirelessly trekking across the alien terrain. The first truly successful pair, Spirit, landed in 2004. Opportunity landed in 2004. They were twin rovers, sent to opposite sides of the planet with a primary mission to follow the water. Designed to last just 90 Martian days, they became the overachievers of the solar system. Spirit explored for 6 years, while Opportunity roamed for an astonishing 14 years, sending back a treasure trove of data. These golf cart-sized explorers were rock hounds, armed with grinders to expose the fresh interiors of rocks and spectrometers to analyze their composition. Opportunity landed in a small crater and almost immediately found tiny, spherical hematite concretions, nicknamed blueberries. On Earth, these formations typically form in the presence of water. Later, it found layered rocks with sulfate salts, another clear sign of a past watery environment. Spirit, on the other side of the planet, found evidence of ancient hot springs. Together, they painted a new picture of early Mars, a world that was not just wet, but possibly had diverse aquatic environments, from shallow salty seas to hydrothermal systems, all of which are compelling places to search for evidence of past life. The success of Spirit and Opportunity paved the way for a bigger, more capable rover, Curiosity. Landing in 2012 using a daredevil sky crane maneuver, this SUV-sized mobile laboratory was a quantum leap in capability. Its destination was Gale Crater, a massive impact basin with a towering mountain of layered sediment at its center. Curiosity's mission was to determine if Mars ever had the right environmental conditions to support microbial life. It carried a sophisticated suite of instruments, including a laser that could vaporize rock from a distance and an internal chemistry lab that could analyze drilled samples. It was designed not just to find where water had been, but to analyze the chemistry of that ancient environment in detail. Curiosity hit the jackpot. Early in its mission, it discovered an ancient streambed, complete with the kind of smooth, rounded pebbles you'd find in a river on Earth. It later drilled into mudstone rocks at a location named Yellowknife Bay and found clay minerals and sulfur compounds. The chemical analysis revealed that this location was once the site of an ancient freshwater lake with a neutral pH, an environment that would have been perfectly habitable for simple microbes on Earth. Curiosity also made the first definitive measurements of organic molecules in Martian rocks, the carbon-based building blocks of life. It didn't find life itself, but it proved beyond a doubt that a habitable environment once existed on Mars. While the rovers get most of the public attention, crawling across the dusty surface, they would be lost without their partners in the sky. The orbiters are the unsung heroes of Mars exploration. The scouts, the mapmakers, the vital communication relays that connect our robotic explorers back to Earth. Missions like NASA's Mars Reconnaissance Orbiter, which arrived in 2006, have revolutionized our understanding from above. It carries the most powerful camera ever sent to another planet. It can resolve features as small as a dinner table. Those images are breathtakingly detailed. They help scientists pick safe and scientifically rich landing sites, including for Perseverance. Orbiting eyes do more than take pretty pictures. They carry instruments that see Mars in different wavelengths, revealing secrets invisible to the human eye. They've made detailed mineral maps, clays, sulfates, other water-related minerals. They track Martian weather, watch giant dust storms form and evolve, monitor the polar ice cap's seasonal growth and retreat. Some orbiters, like MAVEN, study the upper atmosphere, investigating how Mars lost air and water to space over billions of years, transforming it into the cold desert we see today. This orbital infrastructure is critical for tackling one of the biggest challenges, landing. Mars has just enough atmosphere to be a problem, but not enough to be truly helpful. The thin air makes parachutes ineffective, and the heat of entry can melt a spacecraft without a robust heat shield. Engineers have developed incredibly complex, innovative landing systems. The Sky Crane for Curiosity and Perseverance is a prime example. A rocket-powered jetpack hovers over the surface. It gently lowers the rover on cables, then flies off and crashes a safe distance away. That sequence had to work perfectly. There was no room for error. Every mission pushes the engineering envelope. New landers and rovers are heavier and more complex. Dust is a constant menace. It gets into moving parts, coats solar panels, and can whip up into planet-encircling storms. Extreme temperature swings stress materials and electronics. And then there's radiation. With a thin atmosphere and no global magnetic field, Mars is constantly bombarded by high-energy particles that can fry sensitive instruments and would threaten future human explorers. The Perseverance rover, which landed in Jezero Crater in 2021, is the most sophisticated astrobiologist we've ever sent to another world. Jezero Crater was chosen because orbital imagery shows it was once a lake fed by a river that formed a large delta. Perseverance's primary mission is to search for biosignatures in this ancient lakebed. It is gathering dozens of rock and soil samples, sealing them in pristine, pencil-sized tubes, and dropping them at a designated location to be picked up later. This is the first step in the Mars Sample Return Campaign, a joint effort between NASA and the European Space Agency. Retrieve the tubes, launch them into Mars orbit, and bring them back to Earth. On Earth, scientists can probe these samples with instruments the size of rooms, search for definitive signs of past life, date the rocks precisely, and assess the potential toxicity of Martian dust. A successful sample return would trigger a revolution in our understanding of Mars. Perseverance also carried a small helicopter named Ingenuity. Many experts were skeptical about powered flight in Mars's thin atmosphere, but Ingenuity succeeded. Initially planned for 5 test flights, it completed dozens, acting as an aerial scout for the rover and opening the door to future Mars drones. Future aerial explorers could probe canyons, caves, and rugged landscapes inaccessible to rovers. The exploration of Mars is no longer a 2-horse race. It is crowded, international, and even commercial. ESA collaborates on key missions, and China achieved orbiter, lander, and rover, Zhurong, on its first attempt in 2021, signaling a new era of multipolar exploration. Companies like SpaceX are developing powerful, reusable rockets, pushing costs down and capabilities up. Sending humans will demand flawless life support, food production, radiation protection, robust habitats, heavy cargo landings, and learning to live off the land, extracting water and making oxygen and fuel from Mars. The story of our journey to Mars is a story about ourselves, our curiosity, our engineering genius, our audacity. We've replaced myths with data, speculation with scientific understanding,